Hey everybody, today in continuing with Unit 1, we are now looking at describing location in a distribution. So it's a little bit of a shift. We're going to talk about how individuals relate to each other in a distribution by looking at their location. And we'll find a way that we can kind of describe the entire distribution by doing that with a graph of location in a distribution in what's called a cumulative relative frequency graph, or this thing called CRF. So there's a couple of different ways that we can describe location, and the first way is going to be looking at the percentile. So the percentile is giving a location in a distribution, and what it does is it gives the percent of individuals below it in the distribution. So there's a little bit of a debate in the stats community and a couple of different ways that we can define this. Some will look at it as those individuals that take strictly less values or smaller values than the individual we're looking at. That's the way we're going to describe it. Other textbooks and other individuals might say, well, let's go ahead and include that individual. Let's say at or below. But we are looking at strictly below, strictly smaller values than the individual under consideration. Okay? Now, what we need to look at the percentile is, first of all, we need to remind ourselves about frequency and relative frequency. And frequency, remember, is how many individuals take certain values, or maybe even frequency of those taking less than a certain value. And then we have relative frequency, which means we're going to be looking at taking a percentage. So we need to be dividing out of our total number of individuals. And eventually what we're going to get to is this thing called the cumulative relative frequency. Well, cumulative really just means summed. So that means we're going to be adding up all these relative frequencies, and that is going to allow us to see how many individuals or what percentage of individuals take a value below the one that we are looking at. So now let's go ahead and take a look at an example where we are looking at baseball. Below are the win totals for 30 teams in Major League Baseball at the conclusion of the 2019 season. One of the things teams always want to know is, see, how did they stack up? How did they do? Well, if I followed baseball, I would like the San Diego Padres. And the Padres finished with 67 wins. Now, again, I don't particularly follow baseball, so I have no idea if that's really very good. What I can do is, instead of looking at maybe their total number of wins or their win percentage, I want to see where do they stand relative to everybody else that played baseball. So relative to all other teams, how well did they perform? Let's calculate their percentile ranks among MLB teams. So looking at this stem and leaf plot, we can see that, okay, in my stem of 60, there are two teams here that had 67 wins. So which one are the Padres? Well, it actually doesn't matter which one they are, because remember what our definition about percentile means is we want to look at the percentage of individuals that were below the Padres in the distribution. Now that doesn't mean physically, vertically below. That's not what we want. What we want is those that had fewer wins. How many teams had fewer wins than the Padres? So the second team that had 67 wins, they don't count because they had the same number. We are looking at strictly below. So we can see that there's a team with 66, a few more teams with 60, one with 58, and one with 47. So that's not very many teams. Exactly, that is 6 teams. Well, we want to calculate the relative frequency here. So what is 6 out of 30? It's just a simple division problem, right? 6 teams out of the total 30 finished with fewer wins than the Padres. This gives us 0.20. Okay, well 0.20 is not a percentile, that's a proportion of teams. It still tells us the same thing, but what we want to write it as a whole number and in terms of like a percentage. So this would be the 20th percentile. So that means there were only 20% of teams that they performed better than. And that's really not saying very much. That's not very good, right? Let's go ahead and take a look at a little bit more examples and other teams. The Padres play in the National League West Division with 4 other teams. Let's calculate each of their percentile ranks. Okay, so we'll start off with the Los Angeles Dodgers that had 92 wins. So 92 wins, I see that there's just this one team. Now there's a lot of teams that have fewer wins than the Dodgers. We can take a little bit of a shortcut and do something that's related to the complement rule that you might remember from probability in your geometry classes. So instead of looking at those that had fewer wins than the Padres or the Dodgers, let's go ahead and look at how many teams had the same number of wins or more than the Padres or the Dodgers. I'm sorry. So that's 1, 2, 3, 4, 5, 6, 7 teams had the same number of wins as the Dodgers or more. in order to answer my question, I just need to take those 7 and subtract it from 30, and that gives me 23 teams that have fewer wins. And 23 divided by 30 is going to give me 0.76 repeating. And so that would be 0.7666 ... and you might think, oh, okay, well, let's round it and let's put it at the 77th percentile. And we actually decide with percentiles, because of how our definition is, we always want to round down when we're looking at percentile ranks. So that means the Dodgers will have finished in the 76th percentile. And that's going to be a little bit backwards for you, and this is the only time I'm going to ask you to break that rounding convention. But the idea again is what percentage of teams had fewer wins than the Dodgers, and that's 76% of them, not 77%. That's inflating that too much. We'd rather deflate that a little bit, and so that's going to be the 76th percentile. Now, generally, it's not going to be a problem if you make that rounding error and you do round up by that convention that you're normally used to. It's not that big of a deal. But by the letter of the rule, this is what we would do. Let's go ahead and now take a look at the next team, the Colorado Rockies. They had 91 wins, so the Rockies with 91 will be this. We can think about them as being that first team. And this time I'm going to go ahead and count down and see how many teams have fewer wins. So there was 2, another 2 is 4, another 5, that's 9, 11, 13, 16, 19, 20, and 21. Teams had fewer wins than the Rockies, and that gives me 0.7, or puts them in the 70th percentile. I'll leave these next two for you to try and do, and then we can check our answers at the beginning of class. Alright, so at this point what we want to do is try to graph all of these percentiles, and that's going to give us kind of a cool picture of what the distribution looks like based on the location. So it's kind of similar in some ways to a histogram. You can start to see some parallels, and we'll see that in an example in class. But let's go ahead and just jump right into this example, because the best way to actually be able to read a cumulative relative frequency graph that's based on location is to actually build one. Now, the good thing is this is going to be the only time that I'm going to ask you to actually build one of these graphs. It's not very common that you're going to have to do it, okay? I want you to be able to read it, but the best way to be able to read it is to actually build one first. So let's go ahead and do that by looking at a new example. And this one is saying the table and cumulative relative frequency graph below show the distribution of median household incomes for the 50 states and District of Columbia. So the first thing I want to recognize is that's going to tell me if I'm looking at plus Washington, D.C., I have 51 individuals in the distribution, okay? So we have the median household income in thousands of dollars, and this first part here shows me that I had just one state that had a median income between $35,000 to $40,000, and that makes up less than 2% of all of my states and Washington, D.C. Okay, now that on its own is not very illuminating, so now let's go ahead and take a look at the next category. The next category says $40,000 to $45,000 for the median income. And we see that there are 10 states where the median household income was between $40,000 and $45,000. Okay, so what does that tell me then? 10 out of 51 states made or had a median income of $40,000 to $45,000, or 19.61%. Now, that on its own, again, gives me the location of just 10 individuals. That's not really all that different from a histogram. What the CRF does is it takes it one step further by accumulating everybody, and we can start to see ranking a little bit more clearly at this point. So what we want to do when we accumulate, that means we are adding things together. So the cumulative relative frequency, or the cumulative frequency, is saying, go ahead and take that frequency from the previous group and add to it the new group. So 1 plus 10 gives me 11. Okay, and then when we find the cumulative relative frequency is going to say, well, let's go ahead and take the frequency that you had everybody below it and add to it your other frequency, the one in that group. Adding those two together is going to give me the 23.2357. And so what that tells me is I have 23.57% of all my states had an income less than 40 to 45,000. So if it might be a good idea to write that out. Okay, so again, that tells me that 23.57% of all states, that's what I got in this last column, had a median income less than $45,000. So it's strictly looking at the upper boundary of that grouping that we had here. Okay, now we can go ahead and fill out the rest of the table doing the same kind of process. I have 14 states make between 40 to 45 to 50,000. So if I were to add that to my 11 states, I would get 25 states. And 25 divided by 51 gives me 0.4902. Again, going through and doing the same exercise, add 12 to that 25, and I get 37. And then we get 37 divided by 51 gives me that 0.7255. Hopefully you can start to see how we end up filling everything in. The last thing that you want to notice is that your last column, your last entry, should always add up to 1. Every single time. It should be 1 or 100%. Okay? So now what we want to do is do this next part, that's part A, where we draw the cumulative relative frequency graph. Okay, so when we're drawing this graph, on my y-axis I'm always going to have that CRF, and it's going to be in terms of percentiles. Again, CRF for cumulative relative frequency. So that's looking at this last column. This is what we are going to be graphing here. These are the values on the y-axis. Now on the x-axis, we're going to be just looking at these upper boundaries of the median incomes. Okay, so these are the two things that we are going to be graphing. Let's get to it. Okay, so on my y-axis, I have my cumulative relative frequency, and then on my x-axis, I have the median income, and that's in terms of thousands of dollars. And notice I start at 35, because that's my lower bound threshold. There was no state that had a median income less than $35,000. But if I go back up and look at my CRF graph, or my CRF table, I had 0.0196 as my cumulative relative frequency. So that's going to be my y-coordinate, and then my x-coordinate is going to be the end of that boundary, and that was right about here, okay, at 40,000. Next, we look at how many states had less than 45,000 for their median income. Well, that is found here, 0.2357. So we graph 45, 0.2357 for our next graph. 45, 0.2357 is about 23.57%. And that's right about here. Next, we have how many states made less than 50,000? And that's this one, 0.4902. So I'm going to graph 50, 0.4902. That's going to be just below 50 on the y-axis, right about here. Okay. The next one we have is 0.7255, and that was less than 55,000. So I'm going to graph 55.7255. And I'm going to go ahead and speed up the video here and finish out this graphing, but you guys can still be able to see it and follow along with how we make it. Okay. So you notice that I made extra big markers here, and that's just to help me connect the dots, because literally that's what we're going to do next. Now you can use a straight edge if you want, or you can freehand it, it's okay. I'm just going to freehand it. Usually you'll see these done with a straight line or a very smooth curve. That's completely up to the kind of each individual graph maker and how they're going to make it, and also the distribution. So each segment is just going to be connected with a straight line. You will always start down at 0 on the origin in this CRF graph, and you'll always conclude up at the very top of your y-axis at 100%. Every single time you're going to go from 0 to 100. Okay? Now, fun fact about this graph, CRF is also called an ogive. And I think that is a way more fun word, but it's kind of antiquated. Nobody uses ogive anymore, but that's the word for this graph. A cumulative relative frequency graph is also known as an ogive. So impress your friends with all your new cool stats vocabulary. So with this graph, we can see that we are starting to describe the location in a cumulative sense. So it really does get a picture of how the entire distribution changes as the x value increases. Okay. Now, what we want to then do is start to answer some really interesting questions all based off of this. So let's look at part B. Based on your graph, approximately what are the 25th, 50th, and 75th percentiles? So we have 25th, we'll do that in yellow. The 50th, we'll do that in blue. And then green will be the 75th percentile. Okay, and this is just teaching you how to now read this graph. So the 25th percentile, we know that as quartile 1, right? So quartile 1 is at the 25th percentile, but we want to know what's the actual median income for that quartile 1. Well, I'm given the percentile rank. If I'm given the percentile rank, that's where I want to start. And the percentile is at the 25th percentile, and that's going to be right here. So now, go ahead and draw a line that intersects with the graph and no further. And then you want to just go down. And we see about where does that land, and that's right at about 45. Maybe it's a little bit past it because of the thickness of my highlighter here. So let's go ahead and call that quartile 1. We'll go ahead and call that at about 45,500. Again, we use the approximate symbol to indicate that this is just an estimate. It's approximate, but that's quartile 1. Okay, so for the entire US, we could say like the median income, like it's going to change state by state, but 25% of our states, their median income is actually less than $45,000. And that's pretty bad. That's not a very high median income, right? So now let's go ahead and look at the next one. The next one's going to be quartile 2. We know that as the median. So it's like what splits the whole distribution in half. And we're talking about the percentile, which is going to be on the y-axis. So splitting in that in half is going to be at the 50th percentile. And we'll go ahead and again draw to where it intersects. And then we're going to go ahead and go down. And we look like we are right at about 50,000. So again, we can just use this as an approximation that quartile 2 is at approximately $50,000 for that median income. So half of our states have a median income of about $50,000. Now let's look at quartile 3. Well, quartile 3 is again that 75th percentile. So looking at the 75th percentile, that's going to be right here on our y-axis. And we'll go ahead and draw, I'm going to try and draw as narrowly as I can. And that intersects the graph right here. And then we just want to drop down. And that's between 55 and 60,000, but on the lower end. So that looks to me like that's right at about 56, 57,000, somewhere around there, maybe 56,500. That's a good approximation. Why not? So we could say that quartile 3 is going to be 56,500. All right, so now let's go ahead and take a look at our next question. Now we get to actually work backwards from what we did before. We are now looking at Alaska. Alaska's median income is given to us now, and that's $68,426. And we want to know what is the approximate percentile. So now notice that we are given the value that's on the x-axis. We're given $68,426, and we can put that right at about here. Okay. Then we want to find the percentile. So now instead of starting on the y-axis and going across and down, we are going to start on the x-axis, go up, and then across. And so we're looking to see where is this going to intersect, and it's going to intersect right about there, and then we just need to go all the way across, and that is so close to 100. That looks like that might be in the 98th or the 99th percentile. Okay, so we could say that Alaska, their median income is at about the 99th percentile. They are at the top, right? Again, this is just an approximation. Okay, so you can even label this if you want to, that's a little bit easier for us to see. Okay, next one we have is New Mexico. Now New Mexico's median household income is about $43,872. So where does New Mexico fall among everybody else? Alaska was very high. They tend to make a lot more money in Alaska than anybody else does in the US. So let's take a look at where's New Mexico. New Mexico's down here at 43,872. And we'll just go ahead and draw our vertical line going up to see where does it intersect with the actual graph, and then we'll go across, and that looks like that's right about 17th or 18th percentile. So this is New Mexico, and New Mexico is not doing as well. When you're in New Mexico, it looks like you're tending not to make as much money, so that is going to be at the about 17th, maybe, percentile. 17th or 18th, either way would get you there. Okay? Now, that is how you read these CRF graphs, or the ogives, and how you start to be able to interpret and answer lots of interesting questions to see where does a particular individual rank. You're going to remember seeing these when you're looking at, like, say, your ACT scores or your SAT scores. The percentile shows you where you stand relative to everybody else. The next thing we want to do is look at how can we look at this not by percentile but by a different way, and that's by using standard deviation. So this is our final part of the lecture, and this is talking about using what's known as a z-score to describe location. And this is very closely related to our mean and standard deviation. So percentiles was related to median and the IQR. Now we have one that goes with mean and standard deviation. Makes sense. What we want to do with this a lot of times, this is really handy when we're trying to compare two individuals that are really profoundly different. Okay, and so the way we do that is by standardizing. What we do is we eliminate the units of observation to see relative position within a data set. So that's what standardizing is going to do. It's allow you to see relative position, and it can help you to compare unlike individuals. CRF was great when we were comparing state by state, right? But what if we have two individuals that are profoundly different? Can we still describe and compare them? And yes, we can. We do that by standardizing. And what standardizing does is it gives us the standard score. The standard score tells us how many standard deviations an observation is away from the mean. That's what the standard score is. And the notation we use for the standard score is this fun guy, Z. This is one of my favorite things in statistics. It's a super simple formula, and it can do so much for us, and we will use it a ton. So, standard score, also known as the z-score or the standard value. This is the one that I will tend to use. The AP test likes to throw in standard value every now and again, but Z is the best way. Okay, how to calculate a z-score? Well, how do we do this? Well, if we're looking at how many standard deviations we are away from the mean, we start off by saying, well, let's take our individual, that's X, and we need to see how far away from the mean it is. So we take away the mean. That's how we see distance. We do some kind of subtraction. So we say X minus mu, the individual, the observed value, minus the mean, and then we divide it by standard deviations, because what we need to do is put it in terms of standard deviations. Okay, and we are dividing by standard deviations. So super simple. Z is X minus mu over sigma. Z is X minus mu over sigma. Super useful formula, super simple to do, can answer so many questions, and we are going to use this in about 87 different contexts. So if there's one thing that I want you to remember from this year, it is Z equals X minus mu over sigma. Please, 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 please do not forget Z equals X minus mu over sigma. All right, let's go ahead and put it into practice. Alright, so here's our example. Full disclosure, I'm from the Midwest. I'm from Iowa, and in a lot of small town Iowa, which I'm not from, but in a lot of small town Iowa and Midwestern cultures, there is farming out the wazoo, right? Farming is a big deal. And one of the most exciting times of year is when the county fair comes at the end of the summer. And this is where farmers will be able to show off their livestock and what they grow and say, like, hey, you should buy from me. You should buy my corn, my beans. You should buy my cows, my pigs. Look at my horses. Look at my sheep. These are by far the best, right? It's a showcase for all of the farmers in the area, right? So one of the ways that we like to do this, we think, how can we decide who is really the best? Okay, and they award blue ribbons or best in show. If you've read Charlotte's Web, then you know what I'm talking about by talking about who gets best in show, who gets that blue ribbon, right? Well, what if I wanted to look at just which is the absolute best animal, regardless of their breed, regardless of their species? How can I compare two things that are drastically unlike? And the way we can do that is with z-scores, okay? So let's say of all the animals at the county fair, I boiled it down to just these two animals. There's one cow and there's one pig. Which is the best? So we're going to reduce this down even more simply and say, let's just look at one key factor, and that factor is going to be their weight. That's my variable of interest. How much does this cow weigh? How much does this pig weigh? Well, it's clearly not very fair to measure our observed cow's weight, 1,600 pounds, versus the pig, and that's 130 pounds. Because obviously the cow would win, right? They are the biggest, they're going to produce the most meat, the cow's the best. Well, that's not very fair to the pig because the pig is 10 times smaller than what the cow is going to look like, right? So what we have to do is instead, we are not going to compare the cow to the pig outright. We are first going to standardize each one, okay? We are going to eliminate the units of measurement of weight, and we're going to turn it into a z-score. So what I want to do is say, well, how odd is my observed cow compared to the average cow of this species? So my average cow is 1,400 pounds, but my observed cow, the one that's under consideration, weighs 1,600 pounds. I also have, from past history, shown the standard deviation. The variability from cow to cow is 125 pounds, and that's typical. Okay, so let's go ahead and calculate the z-score of the cow. And we know that the z-score formula, because you said you were never ever going to forget it, is x minus mu over sigma. And we have z equals my individual cow, 1,600, minus the average cow weight, 1,400, and we're going to divide that by 125. We get 200 over 125, and you usually want to put the z-score, actually you always want to put the z-score in terms of a decimal, and that's going to be 1.6. That's the z-score for the cow. So the z-score for the cow is 1.6. What does that mean? Whoop-de-doo. Well, again, let's go ahead and read what that definition is of standard score. How many standard deviation an observed value is away from the mean. So let's go ahead and write out our interpretation of this z-score for the cow. This cow weight is 1.6 standard deviations above the mean, right? It's a positive value. That means it's above average. So it is unusually heavy, right? Now, why would I say it's unusually heavy? Well, do you remember from previous lectures, we said that I can identify unusual individuals by looking at how many standard deviations away they are from the mean. That's exactly what we're doing now. And if we say that an individual is more than one standard deviation above or below the mean, then they would be considered unusual. Anybody considered 2 standard deviations away from the mean, above or below, would be considered an outlier, right? Thus, this cow is unusually heavy because it's not quite an outlier. It's not more than 2 standard deviations away. It's only 1.6 standard deviations away. So it is unusually heavy. Now, let's go ahead and look at the pig. The pig, we observed, is 130 pounds, and the average pig is 100 pounds with a standard deviation of 10 pounds. So our z-score for the pig, we can say, is 130 minus the average weight of the pig, 100, and we divide it by 10. And that gives me 3, right? Or 30 over 10, which will reduce to 3. So my z-score for the pig is equal to 3. So what does that mean? It means this pig's weight is 3 standard deviations above the mean. Since it's 3 standard deviations above the mean, it's even more than an outlier. It's super duper weird, right? So being 3 standard deviations above the mean, this is one of the most unusual pigs that we have ever seen. We would say it is extremely unusually heavy for a pig. So now what we want to do is try and put this together, compare the z of the cow and the z of the pig. Before we do that, you need to make one very, very key important observation here, right? We had over here, this was pounds minus pounds divided by pounds. Well, what happens when we divide pounds by pounds? They all go away. This is not 1.6 pounds. There's no unit of measurement. We say this is dimensionless. It has no units of measurement. We're taking pounds out of the equation. And the same exact thing happened over here when we did this with the pig. We have pounds divided by pounds, or pounds minus pounds divided by pounds. Those all canceled out. So this, again, is dimensionless. It has no units. So now we are not measuring how unusual is the cow's weight or the pig's weight. We're forgetting about the weight. We're just saying now we are standardizing this to discount the weight relative to their species. We are now able to see, hey, how do they stack up against each other? Which one is more unique relative to their species? And we can say that since the z-score of the pig is greater than the z-score of the cow, it is more unusually heavy. And we would say the pig wins. It is the more abnormal animal because it has the larger z-score. It is further away from the mean than the cow would be. And this is an extremely powerful tool that we're going to use a whole bunch, and you'll see more in examples in class. So that's it. I know this was a long one, but it's a good one. Thanks you guys so much for watching. Have a wonderful day, and I'll see you next time.